In this video, we're going to look at the concept of the mole in chemical equations and percent yield. When we're trying to study the mass relationship in chemical reactions, that is called stoichiometry. Let's consider the following combustion reaction. In the combustion of methane, we are going to have CH4, which is methane, react with two O2s to produce CO2 and two waters. This means that in this reaction, we are reacting one molecule of CH4, two molecules of O2 to produce one molecule of CO2 and two molecules of water. The coefficients in a balanced chemical reaction also represent the molar amounts of each of the components in our chemical reaction present in the chemical equation. So this means that this reaction can also be expressed as 1 mole of CH4 reacts with 2 moles of O2 to create 1 mole of CO2 plus 2 moles of H2O. Let's now observe how we can while using stoichiometry, we can look at the relationships of all the components within our chemical reaction. You can see that in slide 20, we have specific examples and practice problems for what we call stoichiometry problems. Here we have the chemical reaction that we were talking about previously. And additionally, I present to you a flow chart for how we are going to relate each of the substances within our chemical reaction. Let's put it into practice. Question A states, how many moles of oxygen gas will be required to react 1.5 moles of methane? What we are given is moles of a substance. So within our flow chart, this is kind of like standing here where it says moles of A. Because the question is asking about moles of something else. Basically, we are just converting from moles of A to moles of B. We can see that our conversion factor is the mole to mole factor, or the mole to mole fraction. And the mole to mole factor or fraction is just the molar relationship for the components that we have in the question in terms of the coefficient in our chemical reaction. So in letter A, since we are given moles of methane, I'm going to write that amount, 1.5 moles of CH4. The mole to mole factor is going to come from what is the coefficient of methane in my chemical reaction. So when we look closely at it, there's nothing written, so there's a 1, because that's the unit that I'm trying to cancel. I'm going to write in the bottom 1 mole of CH4. The moles that I'm trying to discover is O2. So I look at the coefficient of O2, and because there's a 2, this means that this corresponds to 2 moles of O2. When it comes to units, moles of CH4 cancel with moles of CH4. So when I take 1.5 and multiply it by 2, then that means that in this reaction, if I'm reacting 1.5 moles of CH4, this required 3.0 moles of O2. Let's look at the next practice problem. It states, how many grams of water will be produced when 2.0 moles of CH4 react with excess O2? In this question in particular, what we have is that we are starting with moles of a substance, which in this case is going to be moles of A. The question is asking grams of another substance. So we're going to go from moles of A to moles of B using as our conversion factor the mole to mole factors or the mole to mole factor. Then once you have moles of B, we're going to find grams of B by using the molar mass of B. Let's set up the problem. I'm starting with 2.0 moles of CH4. So then to find the moles of water, I need to look at what is the relationship between water and CH4. Because I'm trying to cancel the moles of CH4, and then the coefficient here for CH4 is a 1. It's not written. I'm going to write it down so at least you guys can see it. Also, CO2 has a 1. Then what we do is that we write 1 mole of CH4 in the bottom. We're trying to relate it to water, so I go back to my chemical reaction and I say, oh, the relationship between CH4 and water is that it is 1 CH4 to 2 waters. So on the top of my fraction, I'm going to write 2 moles of H2O. Because ultimately the question is not wanting moles, but grams of water. I'm going to use the molar mass of water, in this case, substance B, in order to finalize the question. In the way that I'm going to write it in terms of dimensional analysis, because I want to cancel moles of water, I'm going to write 1 mole of H2O. I already pre-calculated the mass of H2O, which means that H2O, its mass is 18.015 grams. When it comes to my units, moles of CH4, cancel with moles of CH4, moles of water with moles of water. And in my calculator, what I have to do is multiply 2.0 times 2 times 18.015. And I need to round this specifically to 2 sig figs because that's the number of sig figs that we started with. So the final answer is 72 grams. Let's look at one more stoichiometry problem. In letter C, it reads, how many grams of O2 must react with excess CH4 to produce 8 grams of carbon dioxide? To solve this problem, we must take into account that we are given grams of a substance, and we need to go all the way to grams of another substance. In order to complete that, we must go and do the following conversions from, in this case, grams of CO2 to moles of CO2, from moles of CO2 to moles of O2, from moles of O2 to grams of O2, which means that we're going to use 1, 2, 3 conversion factors. So when it comes to this, you have 8.0 grams of CO2. And since we have 3 conversion factors, it's easier to just place the 3 fractions. Where does the first fraction come from? You can see that our conversion factor is the molar mass of CO2. I already wrote it down. So in order to accomplish that, what we have to say is, well, 44.009 grams of CO2 equals 1 mole of CO2. So that means that we already converted from grams of a substance to moles of that substance. The next conversion is going to be the mole to mole factor, which comes from the coefficients in the balanced chemical reaction. The relationship between CO2 and O2, as you can see, is 2 to 1, meaning that for every 2 moles of O2, That corresponds to 1 mole of CO2. And remember that I placed them that way because of unit cancellation. In the last portion of this stoichiometry problem, we must convert from moles to grams because the question is asking us for grams. So we need to use the molar mass specifically for O2 in order to get to the final part of the question. When it comes to this, 1 mole of O2 equals 31.980 grams. When it comes to unit cancellation, grams of CO2 cancel with grams of CO2, moles of CO2 with moles of CO2, moles of O2 with moles of O2, and I plug this in my calculator. I do 8.0 times 2 times 31.980. That's the top. And I'm going to divide that by the result of 40.009 times 1 times 1, divided by 44.009. We see our calculator display. We must round it to 2 sig figs because of the value given, and my final answer will be 12 grams. Lastly, we're going to talk about reaction yields. When reactions are carried out, less product is always obtained, or usually it's more correct, than the theoretical yield due to side reactions. The theoretical yield is the mass of product calculating according to stoichiometric relationships within my chemical reaction. The side reactions are going to be reactions that do occur, but they do not give the desired product. So percent yield is going to be a comparison of what we actually got, which is the actual yield, divided by the theoretical, which is how much we should have gotten, times 100%. Let's do a practice problem on how to calculate percent yield. The following problem reads, a chemist wants to produce urea by reacting ammonia and carbon dioxide. The balanced chemical reaction for this is given here. The problem states the chemist reacts 5.00 grams of ammonia with excess CO2, and the yield that they obtained was 5.0 grams of urea, which is given by that chemical formula. Please understand that even though this chemical formula looks different than that, they have the same number of atoms, 1 carbon, 4 hydrogens, 2 nitrogens, and oxygen. It's just different ways to write it. And overall, we need to calculate what is the percent yield. When we are doing such questions, the first thing that we must calculate is going to be theoretically how much, in this case, urea we should have obtained. To do this, we're going to do the mass to mass relationship that we learn how to do for 2 substances within a chemical reaction. To set it up, basically what we're going to say is, well, if I start with 5.0 grams of NH3, and I try to relate that through stoichiometry to urea, let's see how much urea technically we should be obtaining. When we do this, we have to first divide the 5.0 by the molar mass of ammonia, which has already been pre-calculated. This is going to be 17.031 grams of NH3. in 1 mole of NH3. Next, to find the relationship between NH3 and urea, what we have to look is at the coefficients in the balanced chemical reaction. The relationship between NH3 and urea, you can see that is for every 2 moles of NH3, there's 1 mole of urea. So in the bottom of this, I'm going to write 2 moles of NH3. And then on top, I'm going to write what that corresponds to the urea. So 1 mole, the chemical formula for urea is N2CH4O. And lastly, to actually find the grams of urea that I'm supposed to get if I start with 5.0 grams of ammonia, then I'm going to multiply this by the molar mass of urea. So 1 mole goes in the bottom. I'm just going to write the word urea. And then on top, I'm going to write 60.056 grams of urea. I'm just substituting the chemical formula by the word urea. So when I do this calculation, 5.0 times 60.056 divided by 17.031 times 2 times 1, it tells me, if I round it to 2 sig figs, that technically I should have gotten 8.8 grams of urea. In this problem, to calculate percent yield, I'm going to write what the chemist obtained, which was 5.0 grams of urea divided by the theoretical, 8.8 grams of urea times 100%. So if we take 5.0 and divide it by 8.8, and we round it to 2 sig figs, well, times 100%, and then we take that value and we round it to 2 significant figures, we see that this chemist obtained a 57% yield.